Welcome to the AutoML lecture series. Today we will talk about how to choose a NAS search space. We know now that NAS needs a search space to actually perform the search in, but which architectures should be actually included? And the search space is the component that requires the most human expert knowledge. So how deep can a network be? How wide can a network be? What kind of operation layer types do I actually allow within the search space for our neural architecture? Important to note is that a poorly designed search space also limits what NAS can actually find, regardless of the search strategy used. So if I design a very poor search space, allowing only very small linear layers, for example, on an image, the NAS strategy is also not able to find a high-performing architecture then. The key question to answer in the context of search spaces is how can we define a search space that is expressive enough to contain high-performing architectures, yet compact enough to actually be searched efficiently in. Search spaces are the very first step when we want to set up neural architecture search in general. Search space, and then we can do the actual search strategy with the performance estimation strategy. The background here is that the most human expert knowledge is needed, as already mentioned, and the majority is actually task-specific and inspired by manual designed architectures. So I design a search space differently for images than, for example, for audio or text. And the manual design and inspired by the manual design architectures means main pattern being repeated blocks, for example, in ResNet blocks from He et al. In 2016. Which are visualized here on the right-hand side of this slide. So on the left part of the figure, we can see a small block containing two 3x3 convolution with 64 filters, a ReLU nonlinearity between it, and a skip connection as well. This block, ResNet block, the so-called ResNet block, is then stacked several times upon each other, with the input at the bottom of the right-hand side of the image, and this block stacked several times until we reach the amount of 34 layers of the ResNet block. And we can see the different colors mean that we have different amount of filters, keeping the size of the convolutions 3x3 the same. There exist different types of search spaces in neural architecture search, and we will cover all four of them in today's part. So the first one are so-called macro search spaces, where the structure is based on directed acyclic graphs, where we can search for different operation types, layer types, for the duct topology itself, and different hyperparameters as well. The second are so-called chain structured search spaces, where the idea is to have a chain structure, and we search for operation types as well as macro hyperparameters. The third search space is about cell-based search spaces, which is very similar to what we have seen on the slide before, where we search for the cell or for the small blocks and duplicate those blocks or cells several times upon each other and search for the actual topology of the cell as well as the operations. And the fourth search space we will cover in this part are hierarchical search spaces, which are the most flexible types of search spaces, having a very flexible structure, where we can search for the operation type, the topology, as well as different macro hyperparameters. So let's start with the macro search spaces. We have two types of macro search spaces. The first one is to encode the entire architecture, here on the example of a CNN-based search space, NASBot from Kanasami et al. In 2018. Here we have choices between which kind of operation do I want to apply at each node and the actual topology itself. We can choose between different convolutions, different poolings, and fully connected layers with any kind of directed acyclic graph topology. The only constraint here is that the depth of these architectures are at most 28. In contrast to this encoding of the entire architecture, the second type of macro search spaces are just like a variation of macro level hyperparameters. So here we focus on the variations of where and how much, for example, to downsample the spatial resolution throughout the architecture, where we keep the architecture topology and the operation fixed. Here we can see the fixed cell containing skip connections and 3x3 convolution. And the only question the architecture search approach should answer is what kind of channels do I want to use within which cell. So the topology is fixed, the operations itself are fixed. The only question is the resolution. The second search space we will talk about are so-called chain-structured search spaces. They are a very basic variant of search spaces, in some sense the actual simplest and the least constrained one. They allow for an algorithm to iteratively add more nodes and skip connections, which we will see in a moment. They can be also easily adapted to multi-branch networks, allowing for more degrees of freedom. So here we have two examples of chain structured networks. On the left hand side we can see a very simple chain structure. We have at the top the input, we have n layers, which can be 3x3 convolutions, any kind of convolution, a linear layer with some activation and a non-linearity, and at the bottom the output. They are sequentially input from one layer is the output from one layer is the input to the another layer, in a very chain-structured manner, as the name already mentions. On the right-hand side, we have a more complex version. So we allow for multi-branches going in parallel. We allow for different skip connections, more degrees of freedom in general, but still being a chain-structured search space. So we can add skip connections, nodes, all these things here iteratively. The third search space are so-called cell-based search spaces, which are more or less by far the most popular search spaces used in us, and they are inspired by repetitive blocks. For example, the CNN ResNet we have just seen several slides ago. The problem with the two search spaces we have seen before, they can become very big. So the macro search space, for example, can become very big, needing a lot of compute to actually search properly and for large networks to get a good performance of the architectures. And therefore the solution also in human design is to use those repeated blocks in order to just search for the small blocks, or to design the small blocks and repeatedly add them and stack them upon each other several times, creating very powerful large networks. Therefore the search can become tractable, still allowing for a high performance. So what we do here is we design a macro architecture here on the left hand side of the image, where we have the fixed input and we have the fixed amount of normal cell stacking, a reduction cell, normal cell stacking, reduction cell, normal cell stacking, which is then the output. And the only thing we search here within are the normal cells, for example. So how deep can my cell be, how wide, what kind of operations do I want to use, but just like on a very smaller size. And this one is stacked then n times, which is also predefined by the search space itself. So therefore we search over operations in a smaller scale instead of the overall architecture. We can use different types of cells. We can use normal cells or reduction cells, where the reduction cell have the same structure but using different strides. And the last search space we will talk about in this part are hierarchical search spaces. They're kind of an up-and-coming technique and getting more and more important for the search spaces in general and neural architecture search. Since the computations can be relatively tractable, but they can be also very expressive and diverse in this hierarchical search spaces. As we mentioned, for the cell-based search spaces, we have a fixed skeleton, we have a fixed macro architecture, which is human design, and we only search for the cells. In this hierarchical search spaces, we add additional hyperparameters to the skeleton, so the skeleton can also change. So the NAS searches for over the backbone of the network as well. Here we say that we have different motifs at different levels, and each higher level motif are represented as direct acyclic graph of lower level motifs. And a motif can also be represented by language. So the first level, level 1 of the motif, are operation primitives. For example, 3x3 convolution, average putting. So what kind of operation layer types do I actually want to use? And the second level, motifs, combines the level 1 operation primitives with each other. So we have here the example of a 1x1 convolution, a 3x3 convolution, and a 3x3 max pooling. And we want to assemble these different operations with each other, creating eventually a small directed acyclic graph here, like a small duck, where the input goes through a pooling in the 3x3 convolution, and the pooling output is going into a 1x1 convolution, and then we merge the output of the 1x1 and 3x3 convolution together. Having now such a small level 2 duck, the level 3 motifs combines these level 2 motifs. So here on the example of 4 different level 2 motifs, 4 different small ducks, we just want to assemble those, which is the question of how to assemble those. So these are the parts where the actual architecture search comes in. So how can we combine the cells? So the first one is checking for the operations, designing the small cell more or less, and then the combination of the cells. And the hierarchical search spaces eventually allow for actually truly diverse and novel architectures. The summary of this part is the following. We know now that the search spaces need the most human expert knowledge. We talked about 4 different types of search spaces, where the first one, the macro search spaces, are the most flexible ones and can be coupled with other search spaces and can be coupled with other search space types, for example, hierarchical or cell-based search spaces upon each other. The cell-based search spaces are most suitable for easy transferability to other datasets, since we can easily make them larger and larger by just searching for the cell and adapting the skeleton. Hierarchical search spaces are the most expressive search spaces, allowing for truly diverse and novel architectures, but also can face, of course, some issues when we talk about an actual search strategy. So as mentioned at the very beginning, the search space design can also lead to some difficulties for the search strategy itself. It can benefit, it can help, but it can also make the search harder the larger the search space actually is. So therefore, we need to find a balance between the expressivity and the search difficulty in designing a search space. And I hope you learned now a lot about different search spaces, and see you in the next video.